Hi, this is John Backus from Ortho Clinical Diagnostics. I'm Director of Scientific Affairs at Ortho, and I'm going to be talking today about VITROS Microslide technologies and assays. As a first step, I wanted to inform everybody that if you have any questions during my presentation, then please go ahead and ask them within the chat, within the Q&A area. And they will be answered after the talk itself. I'll also be holding a chat at, I guess it would be an hour from now, so noon Eastern Time, 9 a.m. Pacific Time. Anyways, with that, I'd like to start out by giving an overview of what I plan on talking today about. Okay, so what I'm going to be focusing on today is VITROS Microslide technology. I'll be talking about three general sections. The first one will be talking about colorimetric slides for VITROS, but as part of that I'm going to give a background on the VITROS Microslide technology. The focus of this section after the background will be on talking about paraprotein interference, what it is, where it comes from, what assays are affected by it, and how it's minimized using the VITROS Microslide technology. The second section I'll be talking about is the VITROS potentiometric slides for electrolytes and focusing specifically on sodium. And lastly, I'll be talking about the use of the VITROS BBC microslide assay for achieving accurate neonatal bilirubin results. So first, here's kind of a general overview of the microslide technology. This was developed in the late 70s at Kodak, and it leveraged photographic technology. So what you see is that the microslides themselves have a variety of layers, and each of those layers has a function that it performs within the assay itself. Some of the benefits of this technology, in terms of general benefits, are that it's a very well-proven technology. The technology has been in use in clinical labs for about 30 years. It has the potential to significantly reduce a variety of interferences. Some of those I'll be talking about today. And another benefit is that it not only is there no reagent prep, but also there's no water plumbing or drains, which means that you don't require a clean water source. You don't require the ability to plug into a drain, anything along those lines. And in terms of the electrolyte assays, another big benefit is the fact that there's no electrodes to maintain, and I'll talk about that further. So there's three different formats that the microslides are in terms of general formats. The first one is colorimetric, and that'll be the first one I'll talk about. The second is potentiometric for electrolytes, and the third is immunorate. And that third format I won't be speaking about at all today. So, colorimetric microslides. What this slide is showing is kind of a general overview of a microslide. So, as I mentioned, there's a variety of layers. On a given assay, we'll have the number of layers that are required to do the various chemical reactions and other activities that layers do within a slide. In general, slides have a number of layers, including the spreading layer. The sample is applied to the spreading layer, a reagent layer, a registration layer, and a support layer. And I'll be speaking about each of these in a little bit of detail. Okay, so the spreading layer. This allows very small sample volumes on the order of a few microliters to be spread evenly. In a lot of cases, it minimizes interference, and I'll go into that in some detail, by capturing large molecules that can interfere with chemistry reactions. And it also may contain a variety of chemicals that are necessary in order to break up interactions that the molecules of interest have with other molecules. So in the reaction layer, that's typically where the reagents are put that initially react with an analyte to produce a product. Now this may not be the actual detected product. It may actually be an intermediate because some of the chemistry reactions are relatively complicated. And there may or may not be another layer between this and the next layer below it that acts as a semi-permeable membrane in order to only allow select molecules to move on to the next stage. Again, another means of reducing interferences. So the next layer is the registration indication layer. This is where the color itself is formed, and the amount of color that is achieved is proportionate to the analyte that's being measured. And I'll be speaking a little bit more about the actual measurement of this color. The support layer provides a base for the entire slide, and at the same time it's transparent, allowing light to flow through so that you can actually read the color that's developed within the slide. So other layers that are sometimes added include scavenger layers on some slides. Then there are scavenger layers that actually consume potentially interfering species within an assay. And, some examples of this include a scavenger layer for ascorbic acid in the uric acid slide, and for divalent cations in the triglyceride slide. Another layer that can sometimes be present is a masking layer, and this is really only in the bilirubin, the VUBC bilirubin slide, and it masks the color that is present from hemolysis. And the reason that that needs to be done is because the bilirubin itself is being measured in a spectral region that overlaps with hemoglobin, with the heme group of hemoglobin. Okay, so now I'm going to be talking about the actual detection methodology. So if you think about standard homogeneous wet chemistry type assays, then if you're measuring light directly, then you'd be using transmission spectrophotometry, where you pass light through a liquid, and then any interferences that are in the sample will actually also be giving off light signal. In the case of the microslide, then you're actually reflecting light, so you're doing reflectance spectrophotometry. And because of the presence of the spreading layer and the ability to block signal that's coming from analytes within the sample itself, then there's much less interference that is observed in this instance. Again, the VUBC bilirubin assay is a great example of this, where it's extremely insensitive to large amounts of hemoglobin contamination because the hemoglobin does not actually enter the slide. So here's just an electron micrograph of the spreading layer. You can see it's a bunch of latex particles, and what this has the ability to do is actually trap a variety of interference, and I'll be speaking about one of those in particular. So the interference that I'll be talking about is paraprotein. So first, a little bit of background, because this is not something that I know it's not something that I knew a lot about going into researching this area, and I believe that it's a relatively not well recognized area out there. So paraproteinemia is the presence of excessive amounts of monoclonal antibodies in the blood. Those monoclonal immunoglobulins are called paraproteins. and the disease itself is also called monoclonal gammopathy. It's caused by clonal proliferation of B cells, and it's detected typically in gel electrophoresis as a well-defined band. Well, any type of electrophoresis, actually. So paraproteins are present in a number of conditions. I think that the most well-recognized one is multiple myeloma. There's a listing of several here. The most common is actually MGUS, or monoclonal gammopathy of undetermined significance, which is actually quite common in older individuals. The observed prevalence based on the few published studies that are out there is somewhere in the 3 to 4% range, 3 to 4% of all adults over the age of 50, and 6 to 8% of adults over the age of 80. So the individuals that you would be most worrying, would be more likely to worry about, I think, in general, in terms of chemistry assay results, because there's a higher probability of them being incorrect. Those individuals are also the most likely to have this type of interference. So there's a variety of ways in which paraproteins can interfere with chemistry reactions. I think that really the simplest answer is that the majority of the interference is caused by the presence of acidic reagents in a chemistry methodology. When the acidic reagent contacts the sample, the paraproteins precipitate. This can lead to false readings in turbidity-based or colorimetric assays. And whether or not you get a false positive or a false negative is very dependent on how the signal is being read and whether or not a baseline read is being carried out. There's been a lot of literature out there that are looking at paraprotein interference for a number of key analytes, and I think the most well-published analytes in terms of interference are phosphate, HDL, total bilirubin, direct bilirubin, calcium. Actually, calcium is one where there's been some publication of it, but not quite as much as the others. And sodium, because if you have high levels of paraprotein, then you can actually get incorrect results with indirect sodium methods, which I'll be talking about later in another section. So one good question is how common is paraprotein interference? There's really been very little done in the way of controlled studies to look at this. There have been a number of studies where they would find that a number of samples that gave odd results with one platform, and they would use reference methods to compare against. What I'm showing here is a study that actually did a controlled study of a couple of different platforms. They took 88 samples containing paraproteins from 52 patients, and they looked for interference on 3 different assays on these 2 different platforms. 2 of these assays were also assessed on the VITROS slides because the VITROS method has been repeatedly shown to be insensitive to paraprotein interference for the assays that were being measured. So in terms of the prevalence of interference in these paraprotein-containing samples, actually the majority, 2/3, demonstrated interference with at least one of the 6 assays that was being assessed, and 30% of specimens gave spurious results in at least 2 of the assays. In the case of some of the assays, then both false positive and false negative results were seen. As would be expected, none of the samples demonstrated interference in either of the VITROS slide assays that were tested. So now that we've discussed the fact that it's fairly common to have paraprotein interference, I guess another question is can you predict whether or not a sample that has paraproteins is going to demonstrate paraprotein interference in a given assay? And the answer is really there's no good way of doing that. Here's just a quote out of a CME publication on this topic. there's a poor correlation between the type and level of paraproteins and the likelihood of artifactual abnormality. So this is actually a great article, Fictitious Biochemical Measurements Resulting from Hematological Conditions. It details a large number of published incidences of false results in blood assays, and actually the majority of these false results that are listed are due to paraprotein interference. And I'm not sure how well people can actually see the slide that I have here, but if you look at the bottom, then it lists, it actually, this is only part of a table. It lists the conditions, it lists the causes, it lists the assays that have been shown to be affected, and it lists the solutions that have been published in the literature. And what I've highlighted is that for all of these assays shown here, that one of the listed solutions is to use the VITROS Microslide technology for that given assay, either because of the fact that it removes protein, or because, well, actually in the case of all of these, it's because the paraprotein is actually removed before the chemical reaction occurs. So here's a summary of this section on paraprotein interference. Paraproteinemia is a relatively common clinical condition in individuals greater than 50 years old. The main cause of it is a condition known as MGUS, and the prevalence of MGUS is very high in older individuals, ranging in the high single digits in individuals over 80 years old. Paraproteinemia can cause interference in a wide variety of wet chemistry assays. I believe that it's on the order of 20 different assays where this has been published. The interference is unpredictable and can cause both false positive and false negative results, even within a given manufacturer's assay. And probably the best way of reducing this risk in terms of interference on an automated platform is to use the microslide technology, because of the fact that really I don't believe that there's any published evidence that paraproteins directly interfere with the VITROS assays. So I'm going to move on to talk about potentiometric microslides. So first, in terms of what I'll be referring to as indirect ISE or ion selective electrode methods, these methods typically have a multi-use electrode that needs to be rinsed between samples. There's issues related to the need for frequent calibration, manual cleaning to prevent proteins building up and interfering. And really the big thing is that beyond those convenience issues, there's also an issue that there's a dilution of the sample required. And this can cause falsely elevated or falsely reduced values, which is particularly meaningful for sodium. And it can impact the interpretation of sodium results in particular. So when the microslide technology was being developed, then the feeling was that there could be a better way of doing this. And what was developed were potentiometric microslides. There are potentiometric assays for sodium, potassium, and chloride. What you're talking about is you having a disposable electrode, one electrode per test. There's no maintenance. There's no dilution of sample, which is important because of the fact that ensures accuracy of the measurement. So here's a general layout of how the potentiometric microslide is set up. You've got a patient sample and a reference fluid, and then you've got a variety of layers, including an ion selective membrane layer, a reference layer, a silver chloride layer, and a silver layer. and then a paper bridge at the top where the samples are applied. So the system itself delivers equal amounts of reference fluid in the patient sample. The ion selective membrane allows only the ions of interest to pass through the slide. You form two different half cells within the slide, and the silver and silver chloride layer acts as an electrode. You measure the potential and determine the difference between the electrolyte reference fluid, or ERF, and the sample. So now that I've talked about how the VITROS Microslide method, which is a direct method, works, let's talk a little bit about the indirect methods and what I see as the biggest issue with the indirect methods, and that's what's called volume exclusion effect or electrolyte exclusion effect. Essentially what happens is that all indirect methods carry out a significant dilution of the sample is part of the process of getting an accurate result of what's actually in the diluted sample. However, when doing that, then there needs to be assumption about the amount of solids that are in a sample and the displacement of liquid that's carried out by those solids. So by solids, I mean proteins and lipids. The assumption that's made is that all samples contain 7% solids. If a given sample contains more than 7% solids, then after you do a dilution, you're going to end up with an inaccurately low result because of the fact that you actually have more displacement than you anticipate. If the sample contains less than 7% solids, then you'll have an incorrectly high value. Now, in the case of very high protein levels, then they can be, twice, 3 times the assumption. Obviously, you can't have less than 0% solids, so there's a limit to how much of an impact you can have from a reduction in proteins and lipids. Now, the reason this is really important for sodium in particular is because the reference range for sodium is very, very, very narrow. It's plus or minus about 3.5%. So it's 135 to 145 are typically the values that are used. So really that means 140 plus or minus 5 millimolar. So here's just a listing of the potential misclassifications that can occur. You can get pseudonormonatremia. In this case, then if you have low protein, you can get pseudonormonatremia pseudonormonatremia in a patient who truly has hyponatremia or low sodium. In the case of pseudonormonatremia due to high protein, which is the bottom one in the table, then this is a case of a patient who truly has elevated sodium or hypernatremia, and they're read as normal because the indirect method actually reads low. In the case of pseudonormonatremia, the top one is definitely the most common. It's definitely the biggest concern with indirect IC methods in my mind, and I'll explain why. Pseudohypernatremia can occur when you have low protein in a patient who has normal sodium values because of false elevation. The one that I think that people are most familiar with is pseudohyponatremia, and this is where you've got a patient who's got normal sodium levels, or normal natremia, but they've got high protein or lipid levels. So if you have a patient with paraproteinemia, that patient may have very high levels of protein, and you can get, extraordinarily low sodium values. So if the normal range is 135 to 145, you can get somebody who actually has normal sodium levels, and yet what's being measured is on the order of 120 millimolar. So that would be considered severe hyponatremia. Now there are, well actually I'm going to move on because I'm going to probably discuss each of these in a little bit more detail. So I've already kind of gone through this example where you have a true sodium level of right in the center of the normal range. With the direct ISE method, you're going to get that same result. And with an indirect ISE method, in this sample that contains 20% solids, again, something like multiple myeloma, then the indirect method would be giving a sodium level of 120 millimolar, which would be severe hyponatremia. This is, if you have properly implemented laboratory algorithms, you can look at things like ion gaps, and this can be caught. So this is a severely inaccurate result, but it's only a serious issue if it's not identified. And I think that in most cases this is well enough recognized that it is identified. Now on the other side of the coin, pseudonormonatremia, this can occur in patients, as I mentioned, one of the ways this can occur is when you have abnormally low protein and lipid levels in an individual that has hyponatremia. Now, a key point to make here is that there's a population that's a fairly common population where there's a high prevalence of both low protein and lipid levels and hyponatremia. And that's the ICU critical care population. These individuals will, I would say, I believe it's in the 80 to 90% of individuals in the ICU will have below normal levels of protein and lipids. And these individuals also have a fairly high prevalence of hyponatremia, true hyponatremia. So what you end up with is you end up with a situation where you have a significant number of patients who may be being miscategorized, and there's no laboratory algorithm to identify this error. You know, typically what happens is that there are algorithms to catch things that are out of range when they shouldn't be. It's less common to have algorithms that actually identify when something falls within the normal range, but it shouldn't have. So the impact here is that patients with hyponatremia may go untreated. And in a variety of these populations, whether or not it be ICU or heart failure patients, and there's very clear linkage between hyponatremia and poor outcomes. So, you know, obviously part of that could be underdiagnosis, or should I say it could be exacerbated by underdiagnosis. So this is a really significant issue from the perspective of patients not being treated when they should be treated. So here's an example. You've got a sample that has 3% solids versus a standard of 7%. And so in a patient with a true sodium level of 132 millimolar, that would be considered mild hyponatremia. The direct ISE method reads it as 132, and the indirect method reads it as 136, which falls into the lower end of the normal range. Another example that would be very similar would be a patient who has severe hyponatremia, say 128 millimolar, would be read as 128 with the direct ISE method, and with the indirect method, then they would be read as 132. Now the challenge is that, you know, if you have somebody with severe hyponatremia versus mild hyponatremia, then the way that you actually balance their sodium level or the aggressiveness with which you take steps to balance their sodium level is very different. With somebody with severe hyponatremia, then you need to go through a fairly defined pathway to minimize the risk of poor outcomes due to the process of trying to bring up their sodium level. So in terms of literature evidence for pseudonormonatremia, there's three independent studies, third-party studies, that have independently concluded that indirect ISE methods generally overestimate sodium values in critical care patients. The magnitude of the overestimation in a couple of these publications, they directly showed that it was proportional to the level of hypoproteinemia or hypoalbuminemia in one case. Overestimation by indirect methods in these studies was shown to miscategorize, and when I say miscategorize, this is kind of into buckets of hyponatremic, normal, and hypernatremic. Just using those three buckets, then 20 to 30% of individuals in the ICU can be misclassified. And this is really due to a combination of two things. One, the majority of them actually do have hypoproteinemia, and two, a significant proportion of them actually have true hyponatremia. So those that have true hyponatremia, a lot of those will be read as normal, and those that are normal, a significant proportion of them will be read as hypernatremic. All right, so now I'm going to move on to the third topic of this session, and this is talking about using the VITROS BBC slide for measurement of bilirubin in neonates. So there's a little bit of background. Traditional bilirubin methods, you'll hear them referred to as diazo methods. The diazo reaction was first applied to bilirubin in 1916 by Vanderberg and Mueller, and the conjugated bilirubin reacts rapidly, and unconjugated bilirubin reacts slowly unless you have an accelerator such as caffeine or something like that to unfold and solubilize the molecule. And this is really the basis of the D-bil assay. So if you have a D-bil assay, then you don't have an accelerator. If you have a T-bil or total bilirubin assay, then you do have an accelerator. So the T-bil assay is typically called a JG method, or a modified Gendrastic Groth method, which is diazo with caffeine and is an accelerator. And the T-bil slide, the VITROS T-bil Microslide, is a diazo-based T-bil method. So in terms of D-bil reactions, then what's been done is an effort to optimize conditions to minimize the reactivity of the D-bil assay with unconjugated bilirubin. However, even under optimal conditions, D-bil assays do give false reactivity in neonatal samples containing only unconjugated bilirubin. And I'll give you the easy proof of that here in a couple of slides. So the VITROS BBC slide for neonatal testing actually carries out a direct measurement of conjugated and unconjugated bilirubin, and it correlates to HPLC. In terms of the layout of the slide itself, then what you've got is you've got a spreading layer that contains caffeine, so it releases effectively all of the bilirubin that's not tightly bound to albumin. Now, one difference between this and a T-bil assay is the T-bil assay, the spreading layer on, for instance, the T-bil slide contains a chemical that actually releases all bilirubin from albumin. In the case of the BBC slide, then bilirubin that's tightly bound to albumin, which is conjugated, which is a subset of conjugated bilirubin, will not actually enter the slide. Now, this is something that needs to be accounted for in adults, but for neonates, they really have no albumin-bound bilirubin. So essentially, adding up the unconjugated and conjugated bilirubin that actually enter into the slide does give you a measurement of total bilirubin. So after the sample has gone through the spreading layer, which blocks hemoglobin from entering the slide as well, through a masking layer that, well, through the combination of it not entering the spreading layer and there being a masking layer below the spreading layer, then the sample contacts what's called a mordant, which binds to the bilirubin, both unconjugated and conjugated, and actually changes the wavelength at which these molecules are read. So if you look here, then this is kind of the principle of the BBC slide. What you'll see is that at 400 nanometers, that both unconjugated bilirubin, or BU, and conjugated bilirubin, BC, they give the same reflectance. You'll see that as you go up to higher wavelengths, then you see a higher signal for unconjugated bilirubin versus conjugated bilirubin. So by reading at a lower wavelength, such as 400, and a higher wavelength, in this case 460, then you can actually get a measurement of total bilirubin, and then you have the information that's necessary in order to deconvolve the spectra into what proportion of it is due to unconjugated bilirubin versus conjugated bilirubin. So this is a relatively complicated slide. I'm going to take a moment to go through it. So if you think about it from the perspective of what's actually present in a sample, there's a couple of different species that can be present in, let's say, an adult sample. You can have unconjugated bilirubin. You can have conjugated bilirubin. The conjugated bilirubin can either be singly conjugated or doubly conjugated. A subset of the conjugated bilirubin can actually be tightly bound to albumin. The literature would say that that's a covalent bond. I would say that the most recent data that we would have would say that that there's some questions that can be raised in terms of whether or not it's a covalent bond versus a very, very tight hydrophobic bond. Anyways, so those are the different methods. I mean, the different species that can be seen, for instance, on HPLC. If you look at traditional diazo-based methods, the T-bill method will see all of these. The direct bilirubin method will see the majority of the conjugated bilirubin, but it will also see a small amount of the unconjugated bilirubin. In contrast, the spectral reading that's done for the BBC slide will separate out unconjugated from conjugated with high specificity. In an adult sample, then any of this delta bilirubin would actually be not enter into the BBC slide. So in order to get a measure of direct in adults, then you would actually need to run both a T-bill slide, which measures all of total, and a BBC slide, and subtract out the unconjugated. Because the unconjugated will all actually go into the BBC slide. Now, in the case of neonates, it's a similar but different story. The simple answer is there is no delta in 99.9999% of babies. They just don't make it. So what you have is primarily unconjugated. In some cases, you will have some conjugated, although, as I'll mention later, I think that people may have a misperception in terms of how frequent the presence of conjugated bilirubin is in neonates, or detectable levels of it. So in the case of the BBC slide, then it's quite simple. You just have BU and BC. In the case of traditional methods, as I mentioned, then you're going to get total, measuring total, and a direct measurement will give you primarily measurement of conjugated, but some measurement of indirect as well. And this is just showing what I just said, that there's this uncertainty where you don't really measure all of the direct, and you do measure a little bit of the indirect. To not belabor that, I'll move on to the next slide. So another point to make about bilirubin is bilirubin is very light sensitive. You know, this is really the basis of phototherapy, but it also affects samples that have been collected in collection tubes, particularly if they haven't been collected and put into amber bottles immediately, amber tubes immediately, or wrapped with foil. What happens when bilirubin is exposed to light, at least in a patient sample, because it is very, from the testing we've done, it does say that it's very dependent on the matrix, but in human serum, then when you expose that sample to light, then the bilirubin will create both configurational and structural isomers. The configurational isomers react with both diazo-based chemistry and appear as native unconjugated bilirubin, or BU, on the BBC slide. So, you know, whether or not it be a wet chemistry method, the VITROS T-bill slide, or the BBC slide, all of those methods will measure configurational isomers essentially at 100%. Now, structural isomers that actually impact all of the assays. In this case, then you form an extra ring, and that molecule will not react with the diazo reagent. On the BBC slide, what happens is you get a spectral shift when you get this structural isomer. So the damaged sample will be measured as if it contains both BU and BC. So this can actually be used to a certain extent as a quality check, and the reason for that is because of the fact that the BBC assay is extremely specific for separating out unconjugated and conjugated bilirubin. So if you have a significant amount of conjugated, that's only going to happen in reality on a very infrequent basis, and when it does, then it's very clinically meaningful. But you may see instances where you get elevation of the BC channel, or the conjugated bilirubin measurement on a BBC slide, simply due to the fact that samples are being mishandled. In terms of the overall measurement, if you think about it as doing a T-bill, the BBC slide is much less impacted by exposure to light relative to diazo methods. So if you get a significant amount of light exposure, you may get, say, a 30% drop in a standard T-bill assay, whereas for the BBC slide, you would get a much smaller drop. But what you would see in conjunction with that drop would be a shifting of some of the signal from the BU channel to the BC channel. So here's kind of a summary of the VITROS BBC slide versus other methods. It measures unconjugated and conjugated bilirubin spectrophotometrically, whereas other methods use diazo-based chemistry, either in the presence or the absence of an accelerant. If in the absence of an accelerant, that would be a D-bill assay, and if in the presence of an accelerant, you'd have a T-bill assay. Direct bilirubin is used as a surrogate for conjugated bilirubin, but it does so with less than perfect specificity. And I'll be talking about that again a little bit further in a minute. So a point that I should emphasize, and this is something that is sometimes an issue for clinicians to believe, is that the vast majority of neonatal sera don't have detectable levels of conjugated bilirubin. So a D-bill measurement in a neonate should be essentially zero most, if not, I mean, definitely the majority of the time. And the challenge is that people are used to seeing a value for a D-bill, so when they switch to a measurement that's more specific, then they need to be sometimes shown the evidence that that method is more specific and that really what they were getting was a false result before. So I've already covered that. The second part, the first part of this comparative summary with what I just said. You know, and this is definitely in the literature, and I'll show it, that next. That the BBC slide really gives a zero result, or essentially zero result, for conjugated bilirubin in the vast majority of normal healthy individuals, including neonates. And lastly, in the summary, then, bilirubin is extremely light sensitive. This light sensitivity impacts diazo methods quantitatively more so than the BBC assay. The BBC assay will have higher signals in light exposed samples relative to diazo methods. Both of them will be less than the true measurement. But the BBC slide will also have kind of the tell, which is that you will have a BC signal if you've had any significant light exposure, which is kind of a red flag. So if you get a significantly positive BC measurement in a neonate who has not undergone phototherapy, then that really strongly suggests that they either that the sample has been exposed to light, or that they really do have conjugated bilirubin, which is actually very clinically important to know. So here's some data from a publication from a group at Kaiser, including actually several thought leaders in the neonatal bilirubin field, demonstrating that the VITROS BBC slide provides a more specific measurement of conjugated bilirubin relative to a standard D-bill assay. And if you just look at this table below, you see the results are pretty striking. That if you compare the measurement of a conjugated bilirubin on the BBC slide to a D-bill assay, almost none of the samples for D-bill have a value of 0, whereas for the conjugated bilirubin measurement, 3/4 of the samples have a measurement of 0, and 95% of them have a measurement of no greater than 0.3. In the case of the D-bill assay, nearly half of them are above 0.3, and you need to get up close to 1 before you get to the point where 95% of them are below that value. Now, in the study, what they were really looking at was whether or not the BBC assay, because it provides a more specific measurement, actually is more clinically predictive of issues, of biliary/liver issues. So the 99th percentile for the conjugated bilirubin method was determined to be 0.5 milligrams per deciliter versus 2.1 for the D-bill method. And here's a quote from the authors: "False positive results are less likely when using conjugated bilirubin than when using direct bilirubin levels, because the conjugated bilirubin measurement is more specific. Only 0.3% of newborns had elevated conjugated bilirubin above of at least 2 but less than 5, and 30% of these had disease, versus a dramatically lower proportion for the D-bill assay. This presentation should be available for download, and the reference is shown at the bottom if you're interested in finding out more. So what they concluded was that using the VITROS BBC assay, if you had a conjugated bilirubin level of greater than 0.5 but less than 2 milligrams per deciliter in a newborn, then you need to rule out infection, because that's a common cause of that, and you should observe the patient closely. In those individuals that are greater than 2 milligrams per deciliter, then you really have to look at the hepatobiliary system, because a high proportion of those neonates are actually are in the process of developing hepatobiliary issues. And with that, I have finished the topics that I wanted to cover. I guess as a general summary, the VITROS Microslide technology is a relatively well-proven technology. It's been in the clinical labs for 30 years. However, it still is differentiated from all other methods in a variety of ways, one of which is the fact that it's really the only method that directly eliminates or dramatically reduces it. It's probably the best I can say. It's kind of one of those theory versus law things. The occurrence of paraprotein interference in a variety of chemistry assays. There's really no other automated chemistry analyzer that is capable of doing a direct electrolyte measurement. And in the case of sodium, then that's really key for a fairly significant population within the hospital. It's also important for, I would say, geriatric patients and heart failure patients as general populations, even outside of the hospital. By using an indirect method, you increase the risk of not catching patients who have true hyponatremia in these settings, or underscoping the severity of the hyponatremia in these settings. And you also run at least a reasonable risk of calling somebody hypernatremic who's normal. So the two sides of this coin, on one side you would be undertreating patients, and on the other side you'd be overtreating patients, both of which are costly and have potential consequences. Lastly, the VITROS method is the only automated chemistry analyzer method that measures bilirubin spectrophotometrically, and thus avoids the issues of D-bil cross-reactivity. And I'm not sure if this was on one of the slides or not, but actually I didn't actually say it. The easy way to prove this to yourself, if you have any questions about it, would be to actually look at CAT survey data for samples, for accuracy samples, particularly ones that have, say 10 or 15 milligrams per deciliter bilirubin, because these samples, the accuracy samples in an N-bil survey, are that they're all unconjugated bilirubin. So any signal on a D-bil assay for those samples is false signal. And whereas the VITROS assay, I would say, as an example, if you had 10 mg per deciliter for VITROS, then you might have an average of 0.1 for D-bil. In surveys that I've looked at, then for other methods at the same concentration, then you'll have anywhere from 0.3 to 0.7 mg per deciliter is the average for given method. So you're talking about a significant amount of false cross-reactivity that limits the clinical utility of a conjugated bilirubin measurement. And obviously the last thing is, since you're running a BBC slide, you're getting a conjugated bilirubin measurement on every neonate, which is great because you've got a method that's extremely specific, actually. So if you get a significant elevation of conjugated bilirubin in a neonate, then you know that you have to look at that patient closer, because either the sample has been degraded by light, or else they have elevated conjugated bilirubin to a level that you really should assess whether or not they have an infection or hepatobiliary issues. And with that, I would like to say thank you to everyone who's attended this talk, and I will field any questions that have come up during the talk. Thank you very much. Okay, I'm looking through some of the questions that have come online. I see online that the VITROS Microslides are used in conjunction with the analyzing systems, but I wonder if any handheld analyzing tools for in-office or at-home use is of interest or in development at Ortho Clinical Diagnostics. It's definitely something that has been discussed. That's about where I would leave it. The one place where I can say that these slides are being used commonly is in the veterinary offices. There's a third party that actually has developed analyzers that run the VITROS slides, and they use them in vet offices for measurements in animals, and there are published reference ranges for VITROS slides for a variety of different animal species. Okay, so that answers that question. Okay, comment about sample size for neonate and point-of-care testing for total and conjugated bilirubin VITROS BBC slide assay. The BBC slide utilizes, I don't know the exact volume, but it's around 10 microliters. And if you use the right types of containers, then really the biggest volume requirement is dead volume that you need to have within the well in order to draw up a sample. Now, so you're probably talking about needing on the order of, I believe, depending on the instrument, probably a minimum of 50 microliters in a tube in order to measure it. If you're running a panel of assays, you know, that benefit is kind of carried across all of those assays, because none of the VITROS Microslide assays use more than, I believe, 16 microliters, and most of them are on the order of 10 or 12 microliters or less. So, you know, you require a very small sample for running even panels of assays, and you know, obviously the BBC slide is only one slide, so there's not two assays to be run. So that's one of the reasons why I think the BBC slide, the VITROS analyzers are very popular in the pediatric setting. It's a combination of having a differentiated bilirubin assay and having a platform that's really designed to handle small sample volumes. Thanks for the question. Thanks for both the questions. All right. And let's see. That looks like it in terms of questions. And there's a couple of comments here that I'll say thank you very much for the comments on the presentation itself. And I see a comment there about making the presentation available with an email address, and I will definitely take care of that. And as I mentioned, there will be a chat. It'll be starting in just a few minutes as soon as I can log off and log back onto that. And again, I'll say thank you very much to everybody who's attended, and have a great rest of the meeting.